Okay, so I kind of cut off that last video. I'm not sure if you saw the whole graph. Guys, you just let the asymptotes guide you. Okay, you know that the rational function, if that's a horizontal line, a horizontal asymptote and a vertical asymptote, our function is just going to hug those the closer we get to them on the x-axis. Okay? So I usually just plot, like I said, I find the vertical asymptote, I plot a point or two to the left of it, a point or two to the right of it, and then let my asymptotes guide me into how those curves look. Okay, let's try this one. Again, I'm going to factor some things here. The bottom factors, I could take an x out, and then it's x squared minus 9. So it looks like I have x, and then x plus 3x minus 3. Up top, looks like I might have 2x and x, 3 and 1. It looks like this should be positive and this should be negative. That gives me 2x squared plus 6x minus 1x. That'll be plus 5x and then minus 3. The reason I'm doing this is to make sure, remember, we want our rational function to be in simplest form so we know which ones are our vertical asymptotes and which ones are not. The domain, let's see, x can't be 0, right? X can't be negative 3, and x can't be 3. However, since these cross out, the only vertical asymptotes are at 0, x equals 0, and x equals 3. I thought it was going to be x equals negative 3 as well, since that's out of the domain. However, the x plus 3 canceled. Okay, so that means x equals negative 3 is not a vertical asymptote, even though it's not in the domain. My vertical asymptotes are simply x equals 0 and x equals 3. Now my horizontal asymptotes, I look at the degrees. This is a second degree divided by a third degree. 2 is less than 3. The numerator's degree is less than the denominator's degree. That means my horizontal asymptote is at y equals 0. Okay, oblique asymptote, none. However, there is going to be a hole in the graph at negative 3 something. Okay, so let's see what happens here. I'm going to plot some points around my vertical asymptotes. So I think I'll plot something to the left of 0, maybe negative 1, something between 0 and 3. Maybe I'll put 1 and 2 in, and then something bigger than 3, maybe 4. And when I plug them in, I'm going to plug them into my original function. Okay, see what you get for those 1, 2, 3, 4 numbers. You can go ahead and pause me if you want. Okay, so I put those in my calculator. When I put negative 1 in here, I got negative 3/4 or negative 0.75. When I put 1 in, I got negative 1/2, etc. So I'm going to graph the point negative 1, negative 3/4. I'm going to graph the point 1, 1/2, and 2, negative 1.5, and 4, 1 3/4. Okay, so what that shows me, again, I'm using my asymptotes to guide me. And I see I'm down here, so I'm not up there. Okay, that should curve a little more, but oh well. And on this side, I'm letting my asymptotes guide me as well. We got a nice little curve happening here. Now, here's an interesting thing that happens, guys. Sometimes we do cross over our horizontal asymptote. Okay, you can cross a horizontal asymptote when your x value is relatively small. Okay, the horizontal asymptote is the limit as x approaches infinity. As x gets really, really big, our graph approaches that number. That doesn't mean that when x is really small, that perhaps it doesn't cross it once. Okay, so anyway, this is the graph of this. Now, what's happening at -3? There should be a hole in the graph, and I didn't plot that. To find out what I'm getting close to, I put -3 in the simplified version. The simplified version would be 2x minus 1 over x minus 3. And if I put -3 in there, I get 2 times -3 is -6, minus 1 is -7. I get -3 times, what's -3 minus 3? -6. -3 times -6, that's positive 18. So -9/18 would be -1/2. So I'm a little bit, -7/18, a little bit bigger than -9/18. So well, here's my hole. That makes sense. Okay, so now your graphing calculator won't show you this. Okay. Whoops, 1, 2, 3. Oops, that hole should be right at -3. Sorry, I'm trying to be. Okay, the point is actually -3, -7/18. It's a hole. Okay. Let me show you what that looks like on Desmos. If we graph the function, they don't really show the asymptotes, but we know the asymptotes are 0, and right here at 3, here, let me graph that. I should probably graph x equals 0 and x equals 3, just to show you those asymptotes. But anyway, what I wanted to say is the point -3 this, if I can get on it. I want you to see that it's a hole. There it is. See the hole? It will show you, but you have to click on it. There's a hole there, -3, undefined. There is no y coordinate that goes with -3 because it's not in the domain. Yet, since the function wasn't simplified completely, and when I did simplify it, I could get rid of the -3, right? X plus 3 divided by x plus 3 canceled. Then even though it's not part of the domain, it's not a vertical asymptote like 0 was and like 3 was. -3, undefined is a hole. Okay? So our domain was x cannot equal 0, and that ended up being a vertical asymptote. X cannot equal 3, that ended up being a vertical asymptote. X cannot equal -3 either, but it's a hole, not an asymptote. Okay? So be careful. If your function's not simplified, then go ahead and simplify it. You still use your function for the domain. You just set that denominator equal to 0. All 3 of them are not in the domain. However, when you're finding your vertical asymptotes, make sure you simplify, and then whatever's left over, whatever doesn't get crossed out, they are vertical asymptotes. X equals 0, x equals 3. The other one that got crossed out ends up being a hole. Okay? So in this one, the only thing we have is that x can't be 0. Okay? That'll be our vertical asymptote because that looks like nothing's going to cancel out of there. So we have our vertical asymptote here. Okay, horizontal asymptotes, there are none. All right. This is a third degree over a second degree. It's bigger. Okay. This is bigger than that. The oblique asymptote or the slant asymptote is what we get when I divide 2x squared into each of these. And I see what's left. Okay. This 4x cubed divided by 2x squared, what would that be? 4 divided by 2 is 2. X cubed over x squared is x. 6x over 2x squared is what? 6 over 2 is 3, so 3 over x plus 1 over 2x squared. What we do is we take anything that does not have a denominator in it. So my oblique asymptote is the line y equals 2x. I ignore the stuff that had a denominator. Okay, y equals 2x. Let's graph that. Up 2 over 1 has a slope of 2, right? Here is my oblique asymptote. You divide the bottom into the top. I could have used, anything. I could have used long division. Since it's a monomial, I just took it into each term. Okay. So now I pick some points around my vertical asymptote. I'm going to pick the point 1 and -1 and see what I get when I put that in for x. When I put 1 in, I have 4 minus 6 is -2 plus 1 is -1 over 2. So I have -1/2. When I put -1 in, I get -4 plus 6. That's 2 plus 1 is 3 over 2. So 1 gave me -1/2. And -1 gave me 1.5. Again, I sort of let my asymptotes guide me here. There was no horizontal asymptote. It just gets closer and closer to this guy. Okay, same thing happens over here. Closer and closer to this guy and this guy. I have this little area here. I wonder if anything, x has to equal 1/2, right? So maybe I'll put 1/2 in too and see what happens. But no, actually 1/2 is, we do have values for it. It's down here. I can't have 2 areas for this function. So I don't have to worry about that. Okay? Don't worry about the part. There doesn't have to be a section of the graph at every little intersection here. Okay, this is the graph of y equals 4x cubed minus 6x plus 1 over 2x squared. Okay, so now you've seen one where there's no horizontal asymptote, but there's an oblique asymptote. You've seen one where the numerator's degree is 1 less than the denominator's degree. So y equals 0 was the horizontal asymptote. And you've seen one where they're the same degree. And then the horizontal asymptote was y equals 3/2. Okay? Your homework in this, guys, is on quizzes. There's a couple different quizzes I want you to do. So I hope you enjoy that, something new. Okay, see you in class.